For section 8.5, we're looking at the properties that come with trapezoids and kites. Now what we've done so far is we've talked about strictly parallelograms and the shapes that are within, we can think of the parallelogram family. If you go back to 8.2, we looked at the properties that came with a parallelogram. 8.3 were the ways to prove you had a parallelogram. 8.4 was rectangle, rhombus, and square. All of them were parallelograms, just special cases. What we're going to see in this section, which coincides to 8.5, are going to look at the non-parallelograms that we also have. Trapezoid and its isosceles trapezoid, and the kite. Now if we go by strictly the definition of a parallelogram, the definition was that opposite sides were parallel. So if we think of these other shapes, it's not going to have both pairs of opposite sides parallel. Now, a trapezoid is still going to have some parallel lines to it. A trapezoid is going to be a quadrilateral with exactly one pair of parallel sides. So if we call this A, B, C, D, the two parallel sides we're going to be talking about would be AB and DC. So those have to be parallel, because if they're parallel, we have a trapezoid. AD and BC will not be parallel, because if they were, we would have a parallelogram, and this again is not a parallelogram. Now we can identify some of the parts of the trapezoid. The bases of the trapezoid are going to be what we've mentioned so far, the parallel sides. So that would be AB and DC. So these are our base. We have one base here and the other base down there. The base angles are going to be angles that share a base or have a base in common. So if we look at what we have, AB makes up a base. One of the two base angles for that would be angle A and angle B. Whereas on base DC, the two base angles would be angle D and angle C. So we have our base angles. Now we're going to keep those as a pair, and we're going to see later on that there is a relationship between them. For right now, in just a regular trapezoid, there's not much we can do with them. Last one we have is the legs, and the legs we're going to think of as the non-parallel sides. So in this case, that would be AD and BC. As long as they're not parallel and AB and DC are, we do have a trapezoid. But for right now, we're just identifying them as the non-parallel sides. So really all we can do so far with the trapezoid is just to identify that there are exactly one pair of parallel sides that exist, AB and DC, and as long as that other set is not parallel, then it's still a trapezoid. We won't quite mention this as we go forward, but if I look at a trapezoid, and this is also a trapezoid we're looking at, even though it may look more like a rectangle or even a parallelogram, I only have one set of parallel sides. I have angle A, and let's say angle D right here. Using the fact that these are parallel lines, and I can almost think of this as a transversal, I know that the measure of angle A plus the measure of angle D will be 180 degrees. Those are going to be supplementary angles. If we think back to our parallel lines, those are really consecutive interior angles, which turned out to be supplementary. Furthermore, we have B and C here, and we know that the measure of angle B plus the measure of angle C will also be 180 degrees. So we can separate them and have supplementary angles on either side of the trapezoid. Now, another trapezoid we have, and this will be a special case, will be an isosceles trapezoid. We have seen isosceles before, and that was when we talked about triangles. If we think back to when we had an isosceles triangle, and if I were to take that isosceles triangle and cut a parallel line across, I would essentially have an isosceles trapezoid, which is what we have here. So this is a trapezoid with congruent legs. before, when we just defined the trapezoid, we said a trapezoid just had those legs. Those are the non-parallel sides. Well, for it to be isosceles, we get that AD is congruent to BC. So these sides are congruent. These are still parallel, but again, these sides would be congruent. Now, theorem 8.14 and 8.15 are talking about the base angles. So our base angles, remember, are share that base or that parallel line. That'd be AB base angles, DC base angles. So 8.14 says if a trapezoid is isosceles, then each pair of base angles is congruent. 8.15 says if a trapezoid has a pair of congruent base angles, then it is an isosceles trapezoid. I'm just going to sum that up as a biconditional statement and say ABCD is an isosceles trapezoid if and only if, remember we use that for biconditional statements, angle A is congruent to angle B and angle D is congruent to angle C. We can mark those here. D and C are congruent, A and B are congruent. And those are our base angles. And we think back to when we even talked about isosceles triangles, we had those sides were the same, so the base angles were the same. Same idea here. These sides are the same, these angles are the same, these sides are the same, these angles are the same. It lets us match them up. Now, keep in mind also, we can cover it up, and we know that A and D are going to be supplementary as well. So thinking ahead, if I knew this angle, it's some value, I could subtract it from 180 to find D. I know this is the same, so I could just keep it to move it over. And then once I found D, I know that's the same, and I could find C. So really in an isosceles triangle, as long as we know one angle, we could in fact find the rest of them. Theorem 8.16 says a trapezoid is isosceles if and only if its diagonals are congruent. So here we're going to say ABCD is an isosceles trapezoid, if and only if AC is congruent to BD. I'm not going to draw those diagonals in my diagram. I'm just going to draw another one here. Make sure we mark it as isosceles. Then draw on those diagonals. Now, this is not a parallelogram. They do not bisect each other. We have seen that diagonals are congruent in a rectangle, but that's just mere coincidence in what we're looking in that sense. It doesn't mean it bisects. It doesn't mean that it's also a rectangle. We're just going to use the fact that they will, in fact, be congruent when we look at the diagonals in an isosceles triangle. Now, the last part we have for a trapezoid is the midsegment of a trapezoid. This works for all trapezoids, not just isosceles. But to have a midsegment of a trapezoid, we're looking at MN being the midsegment. And for that to occur, we would need M and N to both be midpoints on the segment, or the legs on the outside. That'd be AD and BC. So to say MN is a midsegment, we're first assuming that M is a midpoint on AD, N is a midpoint on BC. That puts this segment going through the middle of the trapezoid. Now, if MN is a midsegment, then we know two things from our theorem above. The first thing we know is that it's parallel to each base. Well, let's number these bases before I get too far ahead here. So I have base 1 and base 2. So MN is parallel to AB, as well as MN is parallel to DC. Now, it exists, they're parallel, we can make a note of that. If they had it on a graph, we could look at their slopes to see if they all would have the same slope. But what we're really going to use it for is what it says here. The length is 1/2 the sum of the lengths of the bases. So the midsegment is equal to base 1 plus base 2 divided by 2. Now, let's change to fit the diagram we have. Well, that'd be MN equals AB plus DC divided by 2. We can move that 2 and make it, in fact, mn equals 1/2 AB plus DC, which is the same thing, but kind of fits this a little bit more, 1/2 the sum of the lengths of the bases. The key thing is this is the average of the values. That is what the mid-segment will be. It is also in the middle. So let's look at a few practice problems. The first of which is we're going to look at angles, and this is going to be an isosceles trapezoid. So if I were to look at this trapezoid and just cover up and look at this one side, I know that these two angles are supplementary because I have parallel lines and these are consecutive interiors. With that sense, this is 130 because 50 from 180 is 130. Now, the fact that it's isosceles tells us that 50 is also L and 130 is also M. Let's make sure to realize that is different than if this was just a regular non-isosceles, we should say trapezoid. If I didn't know the legs were the same, I could still figure out that these were supplementary, but I wouldn't necessarily know that these are 50 and 130. They would have to have the same legs. If it's not marked, we don't know what this is. We know they add up to 180, but we can't go any further, so you can't jump across and find them off the other leg if it's not isosceles. Okay, go to this next one. I can cover it up. These two are supplementary, J and K. That makes J 80. But since it's isosceles, the base angles are the same, so I can fill those in. And then our last one, I know L and K are supplementary, so L is 62. We can go across now. J is 118, M is 62. Now remember, they won't always be isosceles. It may be one like this, and you have to use those supplementary angles to solve. Okay, down here we're now looking at the mid-segment, and like we said a moment ago, the mid-segment is equal to the base 1 plus base 2 divided by 2, or 1/2 of the sum. So I'm going to set it up just based on what I know. Mid-segment's x is equal to 19 plus 31 divided by 2. This one can simplify pretty easily. X equals 50 over 2, which is 25. We go to our next one. Now, x is not the mid-segment here. We have to set up the mid-segment by itself, which is 34. That's equal to x plus 43 divided by 2. Now here I have to solve. I want to move that 2 over. I'm going to have to do it with multiplication. Gives me 68 equals x plus 43. I subtract 43 from 68 and I get 25 for my other base. My last one, I have 0.6, 0.5, and x. 0.5 is my mid-segment. That's equal to 0.6 plus x divided by 2. I multiply over the 2, I get 1 equals 0.6 plus x. I subtract, and x is 0.4. Now, maybe you noticed the pattern as we went through these. From 0.6 to 0.5, I went 0.1. I actually decreased 0.1. Then from 0.5 to 0.4, I decreased 0.1 again. Well, it was the same. The second one we did, from 43 to 34, I subtracted 9. Then from 34 to 25, I subtracted 9. I did the same thing. It changed the same amount. Let's look back at the first one. Here, we knew that these two bases are actually 12 apart, but then our answer was 6 from both ends, which is half of 12. This exists in a midpoint, or a mid-segment when we look at it. It's half the distance between them. Half the distance between the bases is the distance to the mid-segment, and the same value goes throughout. For example, if you don't see it yet, let's say I have a mid-segment. I have 10 and 18. I want to find the other base. Well, I could set it up similar to what I did here, but I could also look from 10 to 18, I added 8. From 18 to our next value, we're going to add 8 again, which would be 26. We could check real quick. 26 and 10 added together is 36. Half of that would be 18. So it does fit, but you can use that to help you. Now, that will only work typically when you know numbers. If it was something where I had 3x plus 2, 5x plus something, other values to work with, and I was kind of solving for more of an x value, it doesn't quite work as nicely. But if they give you numbers and you see that shortcut, it is something you can use. Now, that finishes up trapezoids. Let's move on to kites. A kite is not going to have any parallel sides. But what a kite is, it's a quadrilateral with two pairs of consecutive congruent sides. We have to make a note here that opposite sides, though, are not congruent. Now let's see why. So two pairs of consecutive congruent sides. So I have AB and BC are congruent. I'm also going to say that AD and CD are congruent. Now, if I marked it like this and said, okay, maybe opposite sides are the same, that's not a kite. That would be a rhombus, and we'd have to deal with the rhombus, which is also a parallelogram and would fit all those. But we're not doing that. We're outside of that parallelogram family. So that's why our opposite sides can't be the same.
Please call extension 71225. Brian Richardson, please call 71225.
So opposite sides can't be the same, which puts two sides together and another two sides together. Now, our first theorem for a kite says if a quadrilateral is a kite, then its diagonals are perpendicular. So here I'm going to say if ABCD is a kite, then AC is perpendicular to BD. So that is a right angle. We had something similar to this in a rhombus, and also is the case here. What this may open up is, I know these are all right angles, so if I was looking at angle problem, I could use that to help me. It also may open the door for a Pythagorean theorem, which we'll look at shortly. The last one we have is if a quadrilateral is a kite, then exactly one pair of opposite angles are congruent. In this case, we're going to say if ABCD is a kite, then the angles that I have are going to be congruent. They have to be opposite of each other. So I have B and D, A and C. The ones that are going to be congruent are in fact A and C. Now, it can't be both sets, it can't be all of them, because then it would be a parallelogram, which again, we're not having a parallelogram here. But why it might be A and C? I like to think of it as identifying them. It's the angle that shares the non-congruent sides. So A and C, A matches up with these two sides, those are not the same. C matches up with those two sides, those are not the same. We can also think if I took this kite here and folded it on line BD over, it would match up exactly on each side. It would be symmetric. BA and BC would match up, A and C would match up, AD and CD would match up. So that's something we can use to help us to match things up. Now, maybe we're looking at sides, maybe we're looking at angles, but keep that in mind as you look at a kite. So let's do some practice problems with it. The first one is going to require us to use some angles to find missing angle values. Now, we know since this is a four-sided shape that the total for all of them is 360, because that's the interior angles of a quadrilateral. But we also have to use the fact that we know two angles are the same here. In the first one, the two angles that are the same are V and S. And those are the angles that that share the different length sides. So that means V is 75. It matches up. Now, doesn't mean T is necessarily 80, and even though it asks for angle V here, let's find angle T, so we're familiar with the process. So I have 75, 75, and 80. I add those together, and that gives me 230. I subtract it from my total, which is 360, so that leaves me with 130 degrees for angle T. We move to the next one. We have to figure out which angles are the same. Well, R and T are certainly not the same because they gave us those values, and we can see they're not the same. So S and V are. To find S and V, I'm going to combine what I have so far and subtract that from 360 That leaves me with 196. That's the amount I have for each angle, or the angles together. I have to find what each one is, but they're the same, so I can take 196, divide it by 2, and I get 98 degrees. Our last one, we have to identify the angles that are the same. R is between the sides that are not the same. That means T will also be the same. So I have 90, 90, 80. That gives us 260, which we subtract from 360. That leaves us with 100 degrees. Now we go to our last part here, and it says we're going to use theorem 8.18, which had to do with the diagonals being perpendicular, and the Pythagorean theorem to find the side lengths of the kite. Now, we're not looking necessarily for all 4 side lengths. I know that these 2 sides and these 2 sides are the same. So if I just solve this half, find x, y, and y, z, that will be enough because I can just copy over the values. But I'm going to use Pythagorean theorem here. So if I look at just x, y, I have this triangle that I'm looking for x, y. Well, xy squared equals 3 squared plus 3 squared. Hypotenuse squared equals the sum of the lengths squared. Xy squared equals 9 plus 9. Xy squared equals 18. I get xy equals the square root of 18, which we can simplify. 18 is 9 times 2, which I can break apart the 3's, and it becomes 3 root 2. And it goes on both sides. If you notice here also, this is also a 45, 45, 90. These are the same. That is root 2 times the leg. Doesn't ask for that, but it is something good that we are familiar with it. Last one, I need yz squared equals 3 squared plus 5 squared. It's yz squared equals 9 plus 25. Yz squared equals 34. So yz equals the square root of 34. Now we look at 34. That is 2 times 17. I cannot break down the factors, so I'm going to make it root 34 and root 34. Now, if by chance you went through and you found the other sides and you didn't automatically see they were congruent, you'd still get the same value. But again, it saves us time because we do know they match up. Remember, that kite does fold over. Now, as you go forward, make sure as this chapter is finishing up, you're starting to be familiar with all these properties and how they fit. The next section is going to look at using them all together. We have to know how they fit together, and that sometimes the properties that work for in this diagram, such as a trapezoid, also work for an isosceles, or the properties that work for a parallelogram also work for those below it, and we have to start separating them so we can identify them. So good luck.